Hey everyone, today is Lab 3. This is the black hole orbit problem of finding the mass of the black hole. The goal of this lab is first and foremost finding the mass of the orbited black hole. We'll be doing this by finding unknowns based solely on given position data, and finally coding a model, which will give us, back to the first step, the mass of the orbited black hole. First, what are we given? We're given the mass of the orbiting star in kilograms, the black hole position in meters, and a data file with the orbiting star position data. On top of that, we're also given the time step of 1 day, which is 86,400 seconds. What will we need to find the mass of the black hole? Well, the first thing we're going to do is go over Newton's second law and the momentum principle. As you can remember, Newton's second law is the change in velocity over the change in time is equal to the net force divided by the mass. And the momentum principle is equal to the change in momentum over the change in time is equal to the net force. We will also need to talk about the components of motion. Here you can see two equations. The first one saying that the change in momentum over the change in time is equal to the parallel component of momentum plus the perpendicular component of motion. You can see the same equation for net force, and that the parallel component of net force plus the perpendicular component of net force is equal to F net. Something to keep in mind is that the parallel component of momentum has to do with the speeding up or slowing down of an object, while the perpendicular component has to do with the curviness, whether it's curving left or curving right. Now we will have to talk about all of these equations and how to use them to find the mass of the black hole. The first step is finding the velocity. If we have R0 and R2, position 1 and position 2, and we subtract the last one from the first one, divided by the change in time, we'll be given the velocity. Next, we need to find the net force. For that, we need the change in velocity. That's taking velocity 1, subtracting velocity 2. Then we can find, using the equations before, that the change in momentum over the change in time is equal to the net force, which is also equal to mass times the change in velocity, all divided by the change in time. The third step is finding the components of net force. The parallel component of momentum is equal to the magnitude of the change in momentum divided by the change in time times p hat, or the direction of momentum. It also equals the magnitude of momentum final minus the magnitude of momentum initial, all divided by the change in time times the direction of momentum. Then, using our previous equation, we can find that the perpendicular component of momentum is equal to the total momentum, minus the parallel momentum component. Finally, we have to talk about finding the actual mass of the black hole. As we know, net force is equal to the gravitational constant times the mass of the black hole times the mass of the star divided by the magnitude of the radius squared. We can change this around to find that the mass of the black hole is equal to the magnitude of net force times the magnitude of the radius squared divided by the gravitational constant times the mass of the star. From here, we follow the same steps we did before, but we put it into the coding of the model. First step is finding the velocity. As you can see here, we compute the x component of the velocity, and here the y component of the velocity. As simple as we did in the previous slide. The next step is finding the net force. We're using the initial and final velocities to find the initial and final momentums, finding the change in these in order to find the change in momentum over the change in time. And finally, using our equation, we know that the change in momentum over the change in time is equal to F net. Next, we need to find the components. We find p hat, and from there we can find all the pieces, the F net perpendicular, the F net parallel, as we did in a previous slide. Finally, using all the pieces we've used, we can come down to this final function. The mass of the black hole is equal to the magnitude of the net force times the square magnitude of the star position minus black hole position divided by the gravitational constant times the mass of the star. Then we ran the model. When running the model, we are given two things. The first is a picture. Here you can see the black hole, and here the orbit of the star, using the position data given. We're also given a screen which gives all sorts of useful pieces of information, including time and different pieces of force. This last number here is the mass of the black hole. The mass of the black hole is 3.779 times 10 to the 31st kilograms. What does it mean? How are the components of net force different from the components of momentum? That's very simple. The components of force cause the momentum to change. In other words, the parallel component of force is what causes the parallel component of momentum to speed up or slow down. In other words, momentum is a reaction of force. Second, what if? Could you find a different black hole mass using the same givens? Simply no. If you look at the formula used to find the mass, everything in the equation will stay the same and will always give the same answer. There is one black hole for this data. Thank you very much for your time.